Thought to make a subject on what is differentiation. Been meaning to do this for ages. I don't mean just doing dy by dx or sort of f of dash x. I don't mean that, or y dash. That's not what I mean. What I'm saying is what is the process of taking dy by dx or f dash of x or y of x, or sorry, y dash? What does, we can call it y dot even. What does this process do? There are a number of other videos on YouTube that go into differentiation, but none of them actually explain what it's doing, which surprises me. So I thought I'd explain it. Why other people not explaining it is a total mystery. It's basically a measure of gradient, but so basically you have a okay. So if you have a curve, okay. To basically put it simplistically, initially, if it was a circle, okay. Before Isaac Newton and Leibniz, mathematicians have been trying to work out a method of working out the gradient of a point on a line. Like that. You see the circle? They were trying to work out what's the gradient at that point on the line, or at that point on the line. That was what, and Newton and Leibniz came up with a method to solve that, to work out the gradient of a point on the line, and that's what it's basically doing. Sorry, I'll say that again. It's to work out the gradient of the point on the curve, sorry, not a line. The reason I say a line is because you actually draw a tangent across there, okay, or a tangent like that. So they wanted to work out a way of, mathematicians have been trying to work out a way of working out the gradient at the point in the curve, which is basically the gradient of a tangent to the curve, okay? That's what it meant by the line. So what's the gradient of the tangent at that point? What is the gradient of that tangent at that point? And that's what this does, okay? So if you want to work out the gradient of, say, that point there on the curve, okay? You can imagine that's further up, and you take another point here, okay? And you draw a line between them like that, okay? So x, okay, y, how does this work? X, y, and then that's, so that distance there is d, so that's x, okay, plus d, and that's y, so you can write this as so basically what Newton said was, if you slide this point down the curve, so you got the chord here, if you slide this point down here, okay, in the limit as, actually you normally call it h, okay, call it h, that's conventional, call that distance h, okay. So you slide that point down the curve, this tangent, this chord gets shorter and shorter, and eventually its gradient is equal to the gradient of that tangent there at that point on the curve, okay? So as h gets smaller, as the distance, as this slides down, this distance gets smaller, as h gets smaller, eventually the gradient of that is equal to the gradient of that line, okay? So what calculus is doing, it lets you differentiate, what differentiation is doing, it lets you work out the gradient of that line at that point. So it's working out the gradient of that point in the curve, okay? So So you basically f of x equals, you say in the limit of h tends to 0, okay? So you have f of, at this point x, that we should really call that, I suppose, f, if it make more sense, f of x here, and that's f of x plus h there. That's actually f of x there, okay? So that's x, and that's f of x, that's the y value. That's x plus y, the h, and that's f of x plus y there. So f of x plus h minus f of x. The reason I do that is because we know from the gradient of a line, the gradient of a line is given by y2 minus y1 over x2 minus x1. Okay, that's the gradient of any line. If you have a gradient of a line like that in space, it's y2 minus it's y2 minus y1 divided by x2 minus x1. So this is what I'm doing here. y2 minus y1 divided by x plus h minus x. Okay, x2 minus x1. Okay. So, as h tends to 0, that becomes the limit as h tends to 0. Okay, it's in the limit means that as the distance gets smaller, as that distance h gets smaller and smaller, this limits means you're getting a value like that is getting closer and closer and closer to 0, but it never actually gets there. Okay. In my video on the world mile record, the 15-meter world record, I mentioned asymptotic graphs. Okay. Graphs a bit like sort of when something's like that, it goes up like that. Asymptotic means it gets closer and closer and closer to the value, and so it becomes half the value, and then half again, and half again, and half. So it goes to half, then a quarter, then an eighth, and a 16th, and a 32th. So take half, then half, then half, then half, then half, then half, then half. So you take halves forever, you'll never ever get to the x value, okay? But you get nearer and nearer. So, and the limit as h tends to 0. That becomes 0, so you as h tends to, I'm writing a limit in the limit as h tends to 0, that divided by x plus h minus x simply leaves h, okay? The x is cancelled, okay? That's what the limit's right. Sorry, I'm waffling away about this part. Okay, so if you have a value like, if y equals x squared, so what's y dash equal to? Okay, so if I substitute these values into this, so you have so we know that f of x equals x squared, okay? So in the limit as h tends to 0, the function of x is now x plus h, so x plus h squared minus x squared, okay, divided by h, okay? So the function f of x equals x squared, so when f of x plus, the function is x plus h, so you have x plus h squared plus, so x plus h squared minus x squared over h, okay? if you expand all this out, you get x squared plus 2xh plus h squared minus x squared, okay? Those cancel over h, okay? So you get limit of h tends to 0, you get 2x h plus h squared over h, okay? The h is, that factorizes out, so you get limit as h tends to 0 of h over 2x plus h over h. Those cancel to leave limit as h tends to 0, okay? 2x plus h. So as h tends to 0, this becomes 0. That basically leaves you with 2x, okay? Plus 0, which equals 2x. So that's just a demonstration. When you put, if the function is equal to x squared, and you put it through this, which is, I explained how it derived here, okay? When you put this through this, you get the answer 2x, which is, that is 2x is the derivative of x squared, okay? So that's an example. You're sliding, this algebra is sliding the point down to the line to make this, the gradient of this chord equal the gradient of that tangent there, to give you the gradient at the point on the curve, okay? That's what it's doing. And calculus is used throughout engineering, physics, maths, astronomy, biology. It's used in all walks of life, in all walks of science, I should say. Building bridges, building trains, making aircraft fly, making your iPads work. When you use your mobile phone, it's relying on electromagnetic radiation, radio waves, and light as well. But it's mainly relying on electromagnetic radiation, which is using Maxwell's equations for electromagnetism, which is very heavy in calculus. Okay? And a lot of computer theory as well. A lot of it's probably very heavily reliant on calculus, but certainly, yeah, Maxwell's electromagnetic theory of James Clerk Maxwell is very heavily reliant on calculus. And that's how your mobile phone, your iPad, your television, your computer all work. So that's basically calculus. That's what it's doing.